So this is part 3 of our blueprint discussion, and we're going to wrap it up with this video. The first video talked about the basic parts of a blueprint: title block, dimensions, views, revision blocks. Second part kind of went into the nature of prints, their status as a contract between all parties, and some shop math that sometimes used to verify the prints. This third video, we're going to wrap up. We're going to talk about some important steps, and then we're going to look at some interpretations of prints that are important to understand. Some symbols that we'll just explain, and so that when you see them in industry, you'll at least recognize what they are. If you haven't already, go ahead and visit the Pragmatic Metrology website and grab the prints so you can follow along, print one out. That's pragmaticmetrology.com. We'll have I'll be putting all these blueprints there so you can follow along. So let's continue with section number 4 of this video, the important steps. So if you've watched the other blueprint videos so far, you'll know, I've emphasized certain things. And first thing, when you get a part, you're gonna inspect this part, or maybe you're gonna make that part. Grab your blueprint and verify the part number, PM-02, revision A2. Verify that against your traveler, your print. Make sure the physical part matches. Sometimes revisions will add features or move features or even remove features. So if you get the wrong revision, sometimes it can be very obvious that something doesn't line up. When you get your blueprint, verify you have the right number of sheets and any other documents you might need. The blueprint or the router, job traveler, it may reference other documents that you need to do this job. It may reference specific tools, additional instructions, additional requirements. For example, a finish on a blueprint may be stated with just 1 or 2 words, use this finish, but your requirements for inspecting that and defining those requirements might be on another document. So it's not uncommon. And then number 2, when you have your title block, go ahead and review, the standard tolerances, what GD&T standard they're using, what year it was called out, what scale the part was printed at. As I mentioned, I don't recommend you actually hold your part up and say, yeah, it looks good enough. That's not the point, but you can do that for a quick check to see if the part's finished, to communicate something. Look, it's not I can't even get it to line up on the print. It's so out of place. So knowing the scale can be helpful if you want to, especially there's some parts like sheet metal. Sometimes sheet metal will let you do that. They'll just say, look, hold it up to the print. I mean, sheet metal tolerances are crazy. And there may be some other industries that I'm not familiar with, but sometimes that is the way you inspect the part. For a machine part with tight tolerances, no, don't do that. Check out the notes. The notes are always important because the notes are something that is being emphasized about the part. These notes and on the prints that I have as an example are not very important because it's just noting that you can use many different manufacturing methods if you want to. Check the material. So material of parts is usually controlled. They want it to be a certain steel, certain aluminum, certain plastic. They all have important properties. And if you grab the wrong material, then you may have made the part correctly, but it's not going to be usable. Verifying the material usually means verifying the certifications that come with the material. So you won't necessarily be testing the material, but you'll want to verify that, yes, this material came from this lot, and this lot is certified by the supplier to be this specification of material. Surface finish or coating, if you're supposed to have a special surface finish, sometimes that gets overlooked, or a special coating. Masking You know, if there's threads involved, if there's certain assembly surfaces involved, they may want to mask those off. And you're going to look for bleed, look for anywhere where the peeling came off, and look for make sure that they masked it correctly. And then of course just special instructions, which will be special handling, special inspecting instructions, whatever it might be. But those will be usually be notes or be on the job traveler. So that's what I do when I grab a print. I look at all of these and then I get started and I start looking at my tolerances, deciding what gauges I'm going to use, and get going from there. So some interpretations. First of all, you know, you may come across GD&T feature control frames. I'm not going to be doing an in-depth GD&T video. There's so many sources for GD&T out there that for me to do one would just be gratuitous. So check out, look online. There's a lot of great resources, textbooks, pamphlets, you know, there's little pocket books. GD&T is not the most difficult subject. I am planning to do a video about how to inspect GD&T. That's on my plan, but at the moment, it's still only in the planning phase. So we'll see if and when I can get to that, but it is something I want to do. On when you see a call out like this one, true position call out, or actually just position, when you see this position call out, how do you inspect that, right? That's what I want to talk about. But whenever you see this frame here, it'll be a rectangular box and it'll have a symbol. This is a GD&T symbol for position. It will then have a box with the tolerance. In this case, the tolerance is a diameter of 0.014. So it's a circular tolerance. You get a modifying symbol sometimes, which will be an M or an L or many other symbols. Actually, I don't know if other symbols go in here off the top of my head, but this one means maximum material condition. And then you'll have your datums. So you have datum A, datum B, datum C. So this doesn't look like the other features we deal with, you know, the feature control frame in the bottom right corner of the angle block print. But how you interpret this, look into some GD&T. But I'll give you a little bit of an explanation. So again, there's the symbol, tolerance, modifier, and datum references. And your datum references look like, well, I have them highlighted. I don't know how to put it in words, but they're going to be boxed with like an anchor on the bottom, a triangular anchor. Different softwares look a little bit different, so there may be some differences in style, but this is generally what they look like. And to give you a top level basic explanation, a lot of these basic dimensions are not good enough for controlling some features. So GD&T was developed, I think, in the 50s after the Second World War as a way to better control certain features that were critical. And so when you use these symbols, they are overriding many of the other symbols that are there. It kind of turns them into references in some cases, not every case, so don't apply that universally. But for example, this position symbol, this position 0.014, this hole has some locations on it, right? It has, let's see, it has 2.5 from datum C, and it has 1.5 from datum B. If you see that on the paper there. And with these, the tolerances on the 1.005 and the 2.500, those are plus or minus 5 thousandths. So I'll draw this real quick for you, give you a top level position explanation. Let's draw this out. So I just promised you I wouldn't give you an in-depth explanation, but I'm about to do that anyway, at least just for this video and just for this hole. So we're calling out this hole We're calling out that distance at 2.5. And we're calling out from the bottom at 1.005. Okay. And that is to the whole center, right? Anytime you define a hole, I would say most of the time you're defining it to the whole center. So let's zoom in a little bit on the tolerance zone. You get 5 thousandths left and right, and you get 5 thousandths up and down if you're going to use this style of dimensioning. Okay, so this would represent everywhere that that center point could be and be within tolerance. Okay. Now, what the GD&T symbol does the true position symbol at maximum material A, B, C, kind of a haphazard way to draw it. What that does, and actually I put it in the wrong spot. What that does is it gives you a circle, circular tolerance. So you no longer have a square tolerance zone when you're working with true position. Square is pretty much easy for us to think about when we're looking at all the other dimensions. It's up or down, it's left or right. When you see a true position symbol, it actually turns into a circle. And how big that circle is defined here. So that is a diameter of 0.014. So it's a radius of 7 thousandths or a diameter of 14 thousandths. And that's what that symbol means. And that's why we use these symbols. If I wanted a circular tolerance zone using just my orthogonal XY, you can't do it. It's simply easier to develop these symbols and do it that way. So that's why GD&T came about, because this is more desirable. You get a bigger tolerance this way, and everybody's happier with a bigger tolerance, even engineering. So anyway, that's just one quick explanation on GDT, on position symbol. So as I said, whenever you see this frame, there's 12 or 14 GD&T symbols that might replace that position symbol. And there'll be different tolerances. You might have different datums and you might have different modifiers. So it'll look a little different each time, but it'll still be shaped like a rectangle with certain sections. Symbol always goes first. Symbol always goes first, then the tolerance, and then modifiers and datums. So when you're looking at this, when you're inspecting this, a few rules of thumb that I like to tell people is, those datums A, B, and C, right? On the print, they're highlighted there. The back side, the bottom, and this side. Those are all ideal or perfect, right? You're assuming, well, at least from a design perspective, these are your perfect 0, 0, 0 intersects. Now, manufacturing process may not make them perfect. I talked about an example in the last video about sometimes the datums are not made perfect, which affects every feature off of the datum, which is a problem. You generally like your datums to be in good condition, but doesn't always happen. And as I mentioned, the feature control frames override the basic dimension tolerances. So the basic dimensions are still necessary. Like in this example, it's still necessary to have those basic dimensions, because we need to know where the hole goes. So we need to know where the ideal center is. That's what the basic dimensions are for here. But the GD&T defines the tolerance zone. So it overrides the tolerance, but you still need the basics to put the GD&T. And as I'm looking at this, I'm realizing I made a mistake on this print. So by the time you watch this video and download this video, there may be a Rev 3. There may be a Rev 3. I can't show you on the monitor with the print. So what is the mistake I made? If you're experienced in position, you're experienced in GD&T, you'll already know what mistake I made, and I'm feeling a little embarrassed I didn't notice until now. But what I should have done on the print is that, because I added this position symbol at the end as a way to demonstrate a revision box for this video, I forgot to. It's common practice. It's GD&T practice to put a box around our basic dimensions, which is something I didn't do. If you take a look at our print, so if you take a look at our print here, I'll zoom in on the looking at my second monitor, so I'm not crazy. I'm not just leaning in for no reason. If you look at our second print here, I should have put a box around 2.5 and a box around 1.005, because those are, a box around 0.5. Wow, I've just screwed up this whole video. A box around 0.5 to locate this hole. So I've made two mistakes. I'm not going to cut them out because mistakes happen. I'm just going to own up to it. But I should have had a box around the 2.5 and the 0.5, because I want to put a true position requirement on that hole. So I neglected to do that. So I'll have to rev this print up. If this were a real world situation, it would rev up to A3 or B1 or something that makes sense. The second mistake I made was in a little bit more forgiving, although it may have confused you. When I copied down this dimension here, I just copied down the wrong one. So hopefully you can forgive me for that one. It should have been 0.500. So when you put a GD&T tolerance correctly, it should look something like that. And you'll have a circular tolerance zone. All right, let's stop making mistakes and keep going. So feature control frames override the basic dimension of tolerances. So here's some examples, and they're not all position, involve some of the other symbols, but rectangular zones become circles. A waviness in a part, up or down, that becomes restricted to a flat or a parallel section. A taper or a skew on, say, a hole, could have a hole that tapers inward, or some sort of diameter that tapers in one direction or another. Sometimes those are restricted to a perpendicular or a parallel zone. And size and position can be restricted to certain shapes. So a hole, either one of these diameters, an internal diameter or an external diameter, you can say, how round does it have to be? How round is round? Can it have a little egg shape, little elliptical imperfections? In most manufacturing, the faster you make the part, the more of this kind of error you get. And so we control it with a circularity or a cylindricity call out. And that restriction feeds back into the manufacturing method so that it can pass, and it feeds into the inspection method so you can verify it. So feature control frames are really important. And this is kind of an aside, this last bullet point here, GD&T is frequently abused and misunderstood. I did this for 5 years and I never met, you could get 5 people in a group together, all looking at one print, and you couldn't get any one of them to agree on anything related to the GD&T sometimes. It's a tricky subject. The standards that get published, the standards Y14.5 2018 or previous standards or international standards, they publish them with examples. They publish them with examples that kind of look like this part. But the examples that get published are just widgets. They have not a lot of function. They certainly try to pick an example that everyone will understand. So, a shaft, a bearing sleeve, a milled part with holes for bolts. They'll pick those as examples, but a real product, a real manufacturing situation is going to have more complexity most of the time. If you're using GD&T, you're using it because the part is complex or the final assembly is complex. And there hasn't been a lot of standardized training. Not a lot of people read the official documents. They're not free. They're not published for free. Your company has to buy them or you have to buy them. So there's a lot of books that tell you what to do when you see them. But then you've got a lot of people who've been trained through tribal knowledge. I learned from a bunch of people. I've also learned from books and from classes, and I've always gotten different information. And I've gotten it from people I respect and trust. 2 people that I respect and trust have a different interpretation, and then I have a different interpretation. So GD&T is going to be one of the more tricky parts of your career, and people are very opinionated. They're very confident sometimes in what these symbols mean, how to achieve them, how to inspect them, how to apply them, right? Sometimes they're applied wrong. There's sometimes, as an engineer, I can say it's not always clear, what's the best way to use the symbol to achieve what I want? You do your best, and sometimes, hey, people make mistakes. There's millions of engineers out there making prints. So this is kind of an aside just to let you know, this is going to be an area of discussion where you're going to want to clarify things and maybe a source of headaches. Going into the training, I mentioned I'm an engineer. I don't even remember GD&T covered in my classes. Now, this is not to say that they didn't cover it. I'm not saying that. It's more of a reflection of, if they did cover it, it didn't make a lasting impression. And engineers have all kinds of coursework, right? We've got mathematics, chemistries, materials, physics, and our engineering courses, right? Our design courses, our thermodynamics. There's a lot that goes into becoming an engineer, and I really enjoyed it, but I also know some of it didn't stick. It's the nature of the game, and any industry you learn a lot. Some of it sticks, some of it doesn't. And I don't remember GD&T being totally emphasized as much as I saw it in industry, right? I'm seeing it every day in industry. So I learned in industry, I learned on the job. And if you're watching this, you probably had the same experience that I did. So um, just know it's going to be a place to think critically, think creatively, and do your best to conform to the print. As I say, it's still a contract, even if it's a bad contract, still a contract that you're responsible for. So we'll move on. We're going to change subjects entirely. We're going to talk about holes. Now, there's a lot of different ways to call out holes because there's so many different holes. I've tried to show you a cross section of some of the most common that you'll see. On the left there, you've got a through hole, then you have a blind hole, a counterbore, a tapped hole, and a precision hole. What I'm calling a precision hole is just anything that has a tight tolerance diameter and a good surface finish. A precision hole could be milled, bored, turned. I'm not a complete expert on machining, but boring bars or reamers, end mills, anything that leaves a good finish and leaves a precision tolerance. So these are the ways you might see it called out. Different styles. Just know, like for example, the counterbore. There's a 397 through wall. There's a 625 diameter on the top side that goes down 375. The tapped hole, they're going to call out the thread requirements. So this thread is required to be a 3/16 UNC class 2B. I'm planning to do a video on threads where I'll talk about the thread tolerancing. Class 2B is the standard tolerance. There's nothing loose or tight about it. So that gives you some requirements, just seeing 2B. And precision holes will have a tighter tolerance. It'll have a plus or minus association with it. Maybe it'll be unilateral. It might just be a plus. It might just be a minus, which we're going to talk about soon. So for holes, when you're talking about holes, there's some unstated sort of industry accepted parts of inspecting a hole. First of all, a blind hole should not break through. So I drew this blind hole, this second one there, stopping short of poking through for a reason, because it's not supposed to poke through unless it's called that way. Sometimes when you're manufacturing, you're really pushing the limits of what's capable in terms of design, and the machining might punch through when the design didn't intend for it because it's such a small sidewall that gets left over. So you'll want to look for that, because it might be the machine did exactly what it was supposed to do, but the tip just pokes through. Sometimes there's requirements on the angle at the bottom of the tip, whether it's going to be more aggressive or more shallow. But for the most part, you just don't want it to poke through. Depth only applies to the full diameter. So for this one, a blind hole, 0.375 down 1 inch. Well, like I mentioned, the tip, that triangular tip there, doesn't matter. We care about the full diameter going 1 inch, and we care about the tip not breaking through. That's how we decide it. Now, if you drop a caliper depth bar into a hole, if you grab it down on the side, you will get a shallow number, and then as you go deeper into the tip, you'll get a deeper number. So you get two numbers. So what we care about is the full diameter. So if you use a pin gauge is going to check the full diameter. And then watch for walking. So I don't have any I do have a big part. Hold on 1 second. So sometimes when you're making a part out of metal, or it could be any other material industry. This part's got through holes all around it. So sometimes when you want a through hole to poke through one side, it won't go straight through on the other side. Instead, we kind of call it walking. It'll start to poke through, and then it'll go at an angle and poke through at a location you didn't want it to. So the way to check for that is to check both ends, because both ends need to be in tolerance. It's drawn, it'll be drawn to be straight, but a lot of times when you have a void in a through hole and it needs to be the same hole, it might wander off in one direction or another. I've seen it a lot. And even in a solid billet, if you tried to drill all the way through this 4 inches relative to the back here, you just start up here, you end up on the back side, it might still walk through the material and bend, because these, as sharp and as rigid as drill bits are, they can still bend a little bit and still cut, so you won't notice any problems. It's probably, this machine metal parts is the industry I've been in, but other industries probably see the same problem. So check both ends when you're looking for walking. For tapped holes, so this part's got a tapped hole. You're going to check it with a go and a no-go gauge, which we have videos about that for checking holes as well as for go, no-go gauging. The minor diameter is optional. So the minor diameter is going to be the through hole diameter. Some places are going to ask you to check it. Other places are really, to check it on every hole is excessive. It won't be stated on the print most of the time, the through diameter for the thread. So most of the time, checking with the go, no go thread diameter, pitch diameter is going to be satisfactory. Same thing with crest flank angle, other parts of the thread. As inspectors, even internal, external threads, it's difficult to verify that. You need special equipment, and if it's internal, it's next to impossible. What you can do is verify the cutter on some sort of optical method. But for the most part, we have go, no-go gauging. If all of these things are working correctly, the go, no-go gauge will work. If one of them's off, usually there's an issue with the go, no-go. So those go, no-go plug gauges will check a lot of this all at once. So that's why only the thread pitch, the thread diameter, pitch, and class are called out. None of the other details that went into making the thread. But there's an issue where I've experienced an issue. Cut taps and roll taps. If you're not familiar, a cut tap cuts away at the material to make the thread. And the roll tap doesn't do it that way. The roll tap deforms the material. So it's actually an interference sort of pressure. As it's going down, it deforms the material that's left over into a thread. And those use different through hole diameters. So it's possible to drill your through hole using a roll tap, okay? And then put the cut tap in. And what's going to happen there is you're going to have a very loose thread because there's not enough engagement. So another thing to do when you're checking the hole is, it'll go in. How loose is it, right? How much can you move it around? I've seen it happen. If you do the opposite, let's say we drill with a cut tap, and then we try to tap with the roll tap's going to break. It's going to interfere. So you won't ever, as an inspector, you probably won't get that far. Maybe there'll still be a broken tap in there if they bring it to you. But just remember that even though we're not inspecting the minor diameter or the other features, wiggle that gauge, see how loose it is, and you will be verifying the thread. And then last one for tapped hole, or second to last one, depths are minimums. So if you had a depth 0.75 on that tapped hole there, that's a minimum. Now that 0.75, it gets the same title block tolerance, okay, plus or minus. I probably should have called that as a fractional or as a 0.8 to get the most tolerance. If we were talking about this print, for tapped hole depth, you generally want the most tolerance because it's hard to control, and functionally, does it really matter how deep a lot of the threads go? It doesn't usually matter how deep the bolts or the screws go. So generally, you'll see your biggest tolerance and might be the fractional one, a 16th. Usually, that's like a rotation of the tap, which is what the machine can control. But those are minimums usually, right? It's not stated. The true stated nature of it is it's plus or minus. It's just like the title block. But most of the time, people want that at a minimum. They don't want the bolt, going short and sticking out. So if you are going to cheat, if you have to cheat, you want to cheat a little bit deeper without poking through, without affecting any other features. If you can do that without affecting any other features, most of the time people won't care. And again, you should probably get the print cleared up. If you're going to have to go deep, just get it cleared up. It's a simple change, and it'll make everything more efficient. So like if this were a real print, I would change it. But it's just an example. And then last one, verify your depth with a ground flat bolt and caliper. So what that looks like, what that looks like is basically you take a bolt, you grind it flat, whatever manufacturer bolt, there's usually a nose on it that you want to grind flat. And when it's ground flat and it winds down, it'll stop. Okay, so it'll stop at the bottom thread. It might be 0.75 deep. It might be a little shallower or deeper, but eventually it'll stop, and you'll have to measure the length of the bolt and then measure how much is sticking out. And because of the tolerancing involved, that's usually a good way to do it. Hopefully you don't have a tight tolerance, because then you're going to be in, there's really not a better way to do it. There are some precision gauges out there that will do depth, but most cases you don't need to use them. I've never needed to use them. I've run into a couple parts where the depth has really been important, and it's been a bear to really control from manufacturing point and from an inspection point. It's been a real pain, so we try to avoid it. Precision holes. So holes with a tightly controlled diameter tolerance. So here's the list. You could do it with a reamer, an end mill, or a boring bar. What you want to look for that won't necessarily be on the prints is you want to look for taper. So as I mentioned, the holes can taper, or the diameters can taper. You want to look for good surface finish on a tightly controlled diameter, because if it's really rough, you might still get a gauge in there and get a measurement, but if it's rough, you're registering on the high points and you're not picking up all the low points, and that may not be good enough. So you want a good surface finish with no chatter. You want to check for form error. So when you're doing a form error check, let's just look at a hole diameter. Let's call it 0.380. And what this means in terms of our title block tolerance, 5 thousandths. So our diameter needs to stay between 0.375 and 0.385. Okay, so when you're checking with your calipers or your micrometers or your CMMs, whatever distance you get here and here, whatever the lows and the highs are, the way I've drawn it, it looks like this is the low. It's a little bit egg-shaped, and this is the high. Whatever those numbers are need to be in this range, okay? Because this is the tolerance we have, every single hole, okay? So whether it's precision or not, but for precision, it usually matters, because what if I change that to plus or minus 1. And that becomes 379. And that becomes 381. This is going to be harder to manufacture. Right? You're going to need a reamer. You're going to need something more precise. Well, what if I make it bigger? What if I make it 2 inches? Okay, 2 inches, 379. 2 inches, 381. It's going to get harder and harder to control that as it grows. So whether it's an inside diameter or an outside diameter, what you got to do is you look at the tolerance, you figure out your extremes, and you verify every point is in those extremes. So in your head, what you end up having is you get a tolerance zone that's low. You get a tolerance zone that's high, okay? And every point you measure, if this black circle represents the part, every point needs to be in between those. It could be that you've got something kind of egg-shaped and most of it's in, but a little bit's out. It could be something wacky, depending on how much you zoom in. So you want to check multiple places, and I went over a lot of this in the whole inspection video, but so when you get there, we'll talk about it some more. But what I forgot to, before we move on, even though this is not, here we go. This is not called out to be a GD&T call out. This is the same thing as circularity or cylindricity, which are GD&T call outs. When you do this style of check, there's kind of an implied GD&T form error. Even though it's not stated, you're saying every point needs to be within this window, which is exactly what circularity says. Okay, so that's why sometimes when I'm teaching, I say, yeah, there's a form error for that. You checked your diameter in one spot and it passed. But what about the other spots? Because it's not round. It's not perfectly round. Nothing is perfectly round. I mean, except gauges maybe, but you can't assume that. You can't assume it's perfectly round. You have to look. If it's in tolerance 90% of the time, and some of the diameter is out of tolerance, well, it's still not going to work. It's still not going to pass. So something you need to look for. Also with precision holes, you can have a chamfer or a radius. Again, I've talked about this in the whole inspection video, but I'll give you a quick demonstration. So I'll draw a couple of examples. Let's talk about a hole that has a radius at the bottom, and you need to register your gauge on it. If you register your gauge on the radius, you end up getting the wrong diameter. You're supposed to be up here on the sidewall. So make sure you raise up your gauge to avoid the start of the radius. Okay, so check a few places and you might see the low point is registering on the bottom radius. If you had an external part, it could be, there it is. It could be the step shaft here. Right, it could be the step shaft. I'll draw this. Well, any place where the diameter changes will have a radius. Something left over behind from the cutter, the manufacturing process, other processes as well will have it. So if you end up putting your micrometer here, you're going to get a false reading again. You're going to be above the true diameter. So you're going to have to verify this radius is in spec. This is a tightly controlled feature usually. And It might be just be in the title block. I think it's in the title block of our example. Max radius 30 thousandths, but you'll want to get your impact points actually away from the radius. So watch out for that, because it may not be called out on the print specifically, but there will be a radius. Okay. So it's in the title block. Max radius 30 thousandths. There it is. Okay, let's keep going. All right, we're almost at the end. Implied form error. This is pretty much what I just tried to draw. So I was drawing it a little early, but as I mentioned, these are some of the GD&T symbols for straightness, flatness, circularity, and cylindricity. And when you see these, there actually is a very strict GD&T requirement. But when you don't see these, that type of requirement still exists. That 970 plus or minus 1, which is if we change the tolerance of this hole to plus or minus 1, well, that would change the, that would look like the picture on the right side, where on the left side you have a low 0.9697 and high 0.9705, and average, take an average, that's 0.9702. But on the right side, you have a low 0.966, that vertical, wake up. Here we go, sorry. This vertical red line represents the low, and that is a 0.966 diameter. This horizontal red line represents the high. It's the same circle, but it's, it's elliptical shaped. And so it is 0.974, but my average is 970, right? So 4 thousandths below, 4 thousandths above, the average becomes almost perfect. So if you're not looking closely, it could be you used your calipers. Hopefully you wouldn't use a caliper on this precision tolerance, but you could have grabbed here and here and gotten 970 with your caliper. Now, you also could have used the CMM, could have used a gauge pin. Only the 966 would have gone through with a gauge pin, so that would have been obvious. If you use a CMM is going to tell you the low, high, and the average, but if you don't look at that, if you only look at the average, it's going to pass. So this has a form error of 8 thousandths, and that is larger than the tolerance zone. 8 thousandths is larger than our plus or minus 1. So 8 thousandths definitely means it's out of tolerance. We don't even need to know the numbers. But if you see a variation bigger than the tolerance zone, it's definitely out of tolerance. So this feature fails. So this is an implied error. If you look at the print, it doesn't have it. And 970 plus or minus 1 doesn't have any GD&T with it, but it would fail the print. So next up, unilateral tolerances. A lot of tolerances you see are going to be one direction instead of both. A bilateral tolerance is like plus or minus, plus 1 and minus 1, plus 5, minus 5. Sometimes you're only allowed one direction. And the convention is usually involved in assembly to guarantee clearances. So your holes are always going to be plus so that you can definitely assemble, and your shafts are always going to be minus so that you can definitely assemble. So just when you see it this way, you get a tolerance zone from it, and you have a new tolerance. That's all it is. So undefined datums are something that they're implied sometimes, but they're not stated. I created this print and I defined the 3 datums. Sometimes prints don't define the datums, right? I did, but as I mentioned, a designer and engineer can do anything at once. And so um, it may not have defined datums, or it may have multiple datums. You may have features coming from the right side, features coming from the left side, and both of them are horizontal requirements. So sometimes you're going to have to go with those implied datums just based on where the leaders are attached, which surfaces they're attached to, and what center points they reach, or what depths they reach. Perpendicularity is also one where every single 90-degree relationship is not called out, right? 90 degrees is implied, and 90 degrees is going to be controlled by the title block plus or minus 1 degree, but you'll never see it called out. It's just implied. Parallelism, the top of the part, the bottom of the part, the right and the left, they're supposed to be parallel, but they're not called out, okay? So there is some undefined relationships that you're gonna overlook for a long time. Then you're gonna think, oh yeah, I never really have verified that this is perpendicular. What if it's not? Is that why I'm failing this part right now? This feature's not in the right place. Maybe it's not perpendicular and I've been taking it for granted. So there are, the more prints you look at, the more you'll realize there's some symmetry, right? When you look at the step shaft drawing, I've defined this the way the industry defines it. There's nothing special about what I did. But you'll notice they're implied to be on center line, but I don't actually have anything that tells you that. So there's an implied relationship there that won't be called out, and you still have your title block to go with. So you just rely on conventional wisdom, and you know, if you're not sure, ask. Sometimes, I mean, a lot of people take for granted and assume all these diameters are on the same center line, but when you transfer parts, or you make them with the mill, or you do it in a way that people aren't expecting, it happens where they're not on the same center line, and problems can happen. So I'll talk about how to verify that when we do the surface plate stuff, but just remember there is an implied relationship, and you're going to need to verify it, even though it's nothing you can point to. When you're filling out a sheet, you can say, oh yeah, it's not collinear to the datum, whatever datum it is. So one last thing, I don't have a slide for this, but I actually just remembered, it popped into my head. Sometimes datums are not defined, as I said. And what do you do when you're measuring a shaft and you don't have any datums? You want to pick a datum. I've got 5 diameters here. Which one is the datum? Well, the GD&T standards will say, pick the largest diameter. You got to pick something, so it says pick the largest diameter. If it's not stated, your overall is your datum. So remember that. If you need to choose a datum, go ahead and pick the outside. When you're doing a milled part and you need to kind of pick datums, what the GD&T standard says is pick the high points. And what that means is you can take a surface plate and take your datum, whatever imperfections are on this surface. When you put it on the surface plate, it sort of gets the high points. The voids are not picked up. The voids are in the part, but the high points are rested on the surface plate. And I don't have a machinist square here, but when you need to pick perpendicularity, you also grab a machinist square. You'll rest it along one edge, and whatever lines up on the other edge becomes your other datum. So I'll be sure to, when I do talk about GD&T, I'm planning to, I'll be talking about that. But for this video, if you don't have datums, you pick the high points by using a surface plate or a square or an angle block. And in that way, if they're not defined, that's how you're going to have to define them. It's a little more important when you start using more complex features, especially GD&T, like position. It's going to be very important. But if nothing's stated, just try to remember, pick up the high points. Okay, so this will be our last slide in this 3-part video series. So I have some tips and some best practices for you. When you first grab a part, obviously check out the title block, check out your tolerances, go through those steps that I talked about earlier. When you actually get down to starting with the measurement, what I like to do is verify the overall sizes first. So I will grab like overall length with a caliper or whatever tool is necessary, overall length, overall thickness, overall height, that sort of thing. And that's a great way to just verify the part's complete. The part is the part you're looking for. It's not something that's substituted. And it just kind of gets you started, gets you handling the part. I generally get a good feel for the part once I've verified how big it is overall. And then you have a couple options. You can either inspect by view, where you literally just go one view at a time. And that's okay. Actually, I'm gonna go back to the computer. Going view by view is more than acceptable. Here we go. So if you're gonna do that, it's gonna guarantee you don't miss anything. And sometimes I do this on more complex parts. I'll go view by view. I'll do the front view, and I'll grab and I'll do the top view, and then I'll grab and do the right view. And hopefully you've got a good print that has everything kind of defined on one view, and you don't have features defined across views, although that's unavoidable sometimes, and you just got to deal with it. But this will guarantee you don't miss anything. What I don't recommend is you kind of hunt around and just do whatever you think's easiest. Have like a method. The other method that I recommend, if you're not going to go view by view, go feature by feature. And what you want to do is verify the size, verify the location, verify the orientation, and verify the form. So those are the critical parts of every feature. How big is it? Where is it located? Is it pointed, kind of angled, oriented the right direction? Because you can locate something, but it'll be pointing the wrong direction. And then the form error, right? I already talked about circularity or flatness. That may not be stated on the prints, but have a big effect on whether a part passes or not. So, for example, you could do this hole, the center hole. I could say, all right, how big is it? It's 970. How far is it from the B datum? It's 0.5, or sorry, it's 1.005. How big is it from the C datum? How far is it from the C datum? It's 1.490. What was the form error when I measured the diameter? Was there a big plus or minus form error? And is it oriented straight up and down like the print shows, or is it at some angle? You could verify that by checking it from both sides. The location at this end is the same as the location at this end. There's many other ways you can do it. Surface plate will be a great way to do it. A caliper from the bottom here and then the bottom here will be another great way to do it. Still on 0. A while ago, I zeroed this caliper and I didn't re-zero it. So 519 from that side and 518, 519 from that side. So it's oriented pretty well relative to this datum. And then I could do it again from this datum, 1.003, 1.005. So overall, not too bad for the tolerance that we have. So either inspect by view or inspect by feature, but have a plan, okay? So have a methodical plan that you don't miss something, because if you have multiple sheets, You could say, oh, I'm going to go sheet by sheet. Sometimes you don't have that luxury. And then in terms of markup, you can record your measurements on the print if your company allows you. You can record them on some scrap paper, record them on a inspection plan, which I had somewhere. I don't have handy here. You can find it on the, you can find the inspection sheet on the Pragmatic Metrology website. You can record your measurements there. If you're going to get red lines, as I talked about in one of the other videos, make sure they're signed and dated and very clear about the markup there. When it's redlined, it becomes official. Anything less than a red line is not official. And it may, I would say, most cases, it has to be an engineer. I've been in cases where a production manager does it and the production manager has the authority, although that's not always kosher with every manufacturing process. But whatever your company policy is, just follow it for red lines. Feel free to highlight the print. Sometimes that helps. I showed you one slide where I highlighted the datums. I find that to be helpful, highlighting key features. When you find something wrong, highlight that. That's a great visual way to communicate to somebody there's an issue, assuming your company allows it. Most do. If it's a paper print, it's usually disposable. But don't go marking up the masters if they are, if you're, for some reason you're working with the master print, you're not working with a copy that's disposable. And then do your best, keep them clean, keep them folded nicely with these large prints. A lot of people got to handle them, and if they end up so dirty from oil and dirt and chips, and it really degrades the quality of the print and the quality of the inspection you can do. So do your best to keep them clean and folded nicely. It's kind of a very quality thing to say, but it actually, it helps a lot when you can actually legibly read your requirements and not make a mistake. So that's it for me. I want to thank you guys for bearing with me in these 3 videos. Please check out my website, pragmaticmetrology.com, for more videos, the drawings. You may see an updated rev for this by the time you watch it. 3D models for this part, so you could 3D print this or program it and machine it if you like. And I need to thank the Laney Machine Technology College for letting me use this part, providing a lot of the equipment, helping me out in this project. They have a great program. They have many courses in manual machining, CNC, metrology and inspection, quality control, CMMs, CAD programming, CAD modeling, writing CNC programs, mechanical drives, and they even offer certificates, associate's degrees, and apprenticeships. So they're connected to local businesses, and if you're interested in advancing your career, the Laney College in Oakland, Northern California Bay Area, they offer classes in the fall, spring, and summer, and I recommend you check it out if you're interested in advancing your career and getting some more education. So once again, thank you. Check out my website, pragmaticmetrology.com, and look forward to seeing you with the next video. Thank you.